Okay, so let's see. Today we're going to go through the practice tests, and after the class, I'll email the solutions out to you, so you'll have those to go over. And then we have a in-class test on Wednesday. Okay, so I don't think we need to go over I think we kind of did this in class, the basic principles, the first 5. The short answers, we kind of did that, but maybe we do a couple of them. Yeah, let's go through the short answers quickly. I won't have you come up here and write it, but when we get to the imperiometric section, I'm going to ask for volunteers to come up. Yes, ma'am. Volunteering already? That's no.
I have a question.
Okay.
Can you explain the difference between the divergence and the gradient and this use of the triangle symbol?
Sure. Yeah. Okay, the question was to explain the difference between the divergence and the gradient, and the use of the del symbol, or also called the nabla. I'm not sure why. So what is the date today? It's the 8th. Today's the 8th. Yeah. Okay, so this is. It's often written without a vector on top of it, but it is always a so-called vector operator. So it's not a vector in the sense that we understood vectors before, because it is an operator. So it doesn't have a length, for example, or direction clearly defined. It operates on something, and it will operate, for example, on any scalar function, and this produces a vector field. So a scalar field the gradient of the scalar field produces a vector field. And we said this before. This is the direction of greatest increase of f. And then so that's the direction. The magnitude is the slope of f in that direction. And so notice that this is always at least I would say it's virtually always, these are derivatives with respect to position, with respect to the coordinates, x, y, and z. So this is the Cartesian form, and the proper definition is, the primary definition is this, so it's the gradient of f. That's the proper definition of grad, but we can also have applying the same operator to some vector field, and this would be the divergence. And we had that, the primary definition of that is the limit as the volume goes to 0 of the complete surface integral that bounds that volume of the flux of that vector field over the area. Then we shrink wrap, we take the limit as that volume goes to 0. So you're looking at the flux coming out of a point in the limit, and that's the divergence. And again, you can get both of these then from the Cartesian form. The gradient of f is then the partial derivative, the slope of f in each one of these directions. Okay, and the magnitude of this gradient, which is the slope in the direction of greatest increase, is going to be the sum of the squares of the components. Okay, and in Cartesian form, the divergence, you have to know the components of W, or that field, the Cartesian components. And if you have those Cartesian components, which are themselves functions of x, y, and z, then the divergence is the sum of those derivatives. And now there's no direction left. The divergence is a scalar. So the gradient of a scalar is a vector, the divergence of a vector is a scalar. Mr. Picot.
Back to the primary meaning of the gradient.
Yes, sir. These two.
Yeah, the slope of f in that direction.
Yeah.
What do you mean the slope? Like if we're talking like a 3D thing?
Well, well, it's not, you're given one direction, so it's no longer three-dimensional, right? So you figure out in what direction does F increase the most from here. Now, in that direction, what is the rate of increase? What is the rise over the run in that one direction, whatever that direction is? And amazingly enough, I mean, it may be a little surprising that it's that simple. That actually gives you the slope in that direction. Okay? Does that make sense? Okay. Did I answer your question, Ms. Wheeler? Yeah. Do you have, well, both of you, yeah. Do you have any other questions about this operator? So it's not obvious when you start that these two fundamental definitions can be encapsulated in Cartesian form by the same operator. Here, right? It's not obvious from the fundamental definitions that you can encapsulate them with the same operator, but it is true that, and he goes through that in the text to show you that does work. And so you can notice this divergence here is like a dot product. We have this thing that's like a vector operator, and it has the dot product with the form. So hang on a second, Mr. Miller. Let me just point this out. When we take this dot product of the gradient operator or the nabla, take the dot product with the vector field, also expressed in Cartesian form, right? And we expand that out. We have 9 terms, but 6 of them vanish because the dot products of the unit vectors are 0. So you only get the 3 terms in the divergence that you would hear. Okay, Mr. Miller.
So both of them use the same operator. It's with context you're using it in?
Well, you can see from the notation, and I've started writing, for the purposes of this, I've started writing an arrow over the inverted delta, the nabla, the gradient operator. I've started writing a vector over it, but it's always a vector. So you will often see people, textbooks and me, dropping the arrow over the thing. But the context is to determine whether it's, which one it is. This is not a vector, and this is, and there is a dot there. So that's how you see the difference between the gradient and the divergence, because the divergence will be of a vector field, and that dot is very important. It's analogous to, it's a lot like the dot product of 2 vectors, except, of course, the vector operator is not quite a vector. Okay, but as you can see here, when I wrote this out, it ends up being very similar to that. We have the derivative of Wx only in the x direction, and the derivative of Wy only in the y direction. Okay, and the other thing to remember is that the divergence, which is also not quite so obvious from the primary definition of the divergence in words gives you how the vector field changes along its direction. And you can see that here. This is the x component. Well, how does that change along its direction, which is in x? And how does that change along its direction, which is y? And how does this change along its direction, which is z? So that will distinguish it from the curl, which we haven't considered very much yet. We've read about it, but we haven't done exercises in class. The curl will tell you about how the vector changes perpendicular to itself. Okay? And that will be formed by taking the cross product of the gradient operator with the vector field. So just to flesh that out a little bit, in the next chapter we will do that, which is the curl of the vector field. And that will be formed by taking the cross product of the gradient operator with the vector field. And we'll work out all the components, but you could do it right now, pretty much figure it out if you remember the cross product. Any questions about that? So if I give you a scalar, as we're doing here in the practice test, I give you a scalar field or a vector field, you should be able to take the gradient or the divergence of those things in Cartesian form, right? That's just the machinery of doing these things, but you should also have an understanding of what they are. Okay, so the cause of an electric field, quickly, briefly.
Massive charged body.
Yeah, massive charged body, and a body is a generic substance. We talk about it as a generic substance. So a massive charged substance or body. And then we talk about how does one body with charge cause an electrostatic force on another body with charge at a distance away from it. So that's explain the propagation through the parts of the plana from one to the other. Okay, now here's an important thing, the distinction between the electrostatic condition and the electrostatic approximation. So what is the electrostatic condition?
Upwards move.
Nobody moves. Put the charges in place and don't let them rearrange. The electrostatic approximation is what?
Any movement is slow enough that you can negate the propagation time.
That's right. Things move around slowly enough and the distances involved are short enough that you don't need to worry about the propagation. So if I have a charged body here, it generates an electric field here. If this body moves, then you can consider that the electric field over here changes instantaneously. And also the motion is slow enough, we don't need to consider magnetic fields and things like that. Okay, the dimensionality of rho and J. Oops, wrong pen. Dimensionality of rho and the dimensionality of J. And what is the relationship between rho and J?
Current density versus charge density.
Yeah, so this is what is the dimensionality of charge, volume charge density here, right? This is a volume charge density.
Q per length.
Q, right, Q per volume. And this relationship I'm about to write down here will help you to remember the dimensionality of J. If all the charges are moving with the same velocity, all the charges in a certain location are moving with the same velocity, then J is just the product of the volume density and the velocity. And so it's Q per area per time. And I, what is the relationship between I, which is the total current, and J? It's J times an area. I'll put it like that. Yes, and the dimensionality of I is then just Q per time because you multiply by an area. I multiply J by an area. Okay, so if you have a wire that's transmitting some current density in here, I is the total of all that flux coming through the wire. Okay. So, what is Gauss's law? Give both the differential and integral forms. This is also, then the differential form is the way you would see Maxwell's first equation expressed, usually. So, Gauss's law, as opposed to Gauss's theorem. We do this in class? On Friday we did, yeah, right. So I won't go over it again. And Maxwell's third equation, again in the electrostatic limit, meaning nobody moves, so there are no magnetic fields. So we haven't considered yet the curl, but the Maxwell's third equation, when we get to the curl, you'll understand this more completely. But this says that there's no vorticity in the electric field. It simply diverges from, as a result of having charge at that location. That will create a divergence in the electric field, which is the first of Maxwell's equations. If I put a K in here, I can deal with CGS or SI systems. K equals 1 gives me CGS. And K equals 1 over 4 pi epsilon naught is SI. Yes, sir. Mr.
What
McKinney.
does epsilon naught stand for?
Epsilon naught is called permittivity of free space, I think. Permittivity of the vacuum. It comes from what happens in an insulating material. If I apply an electric field to it, it can polarize that material a little bit, and that will partially screen an electric field inside. So a conductor has effectively very high permittivity, permeability. I can't remember which term it is. So it completely screens an electric field. An insulator partially screens an electric field. And that dielectric constant, epsilon, is what we use to represent that. So this is looking at the vacuum as a kind of dielectric material, which but it has no ability to screen. So I think that's the reason for that constant, is historically considering the plana as though it could screen, partially screen. This goes back to Maxwell's understanding of the mechanical ether. I think. I'm not certain of that. I'm speculating here as to the origin of that constant. Of course, you know, what in effect it just comes in as a constant, which changes how you measure charge, units for charge, electric fields, that sort of stuff. Okay. Went to sleep again. Okay. All right, so now let's go on to the imperiometric section. So what I'd like to do is, we can't do all the several people all at once like you did in class in the other room, but we can do two at a time here. So I'm going to have volunteers give the number one is given a charge at some location, x prime, y prime, z prime. Find the electric field and the electrostatic potential at some other point, x, y, z. All in Cartesian form. And okay, and then there are a couple of them that are really simple. So I'm going to say number 7 would be well, yeah, why don't we just go do these in order? Okay, so let's go ahead and do number 2. Given an electric field of measure E vector at some location, what's the force? Okay, so one is really simple. First one is a little longer. So a couple of volunteers, please come on up here. And I'll hand you pens, and you can.
Okay. I'll go with the first one.
Okay. Here's that one. Use that one on there. Okay.
Yeah.
Now that's a cube.
Yes, that is
Okay.
an attempt at a cube.
Okay. All right. Good. All right. Mind your P's and Q's. It looks like a backwards Q. Okay, that's number 2, the force, and so maybe you put a little tail on the Q. That might help. Okay, I'm going to put Mr. Miller's work here. Okay, so that's the electrostatic field, phi. Okay, very good, Mr. Miller. That looks fine. So a short way of writing this is to say that that should be here. Hang on a second. I want to bring up the. Oh yeah, right. Oh, I didn't want to do that. Trying to select the pen. There's 2 different versions of OneNote on this thing. One is the mobile version, and the other is the desktop version. And I can't get used to switching back and forth, so I'm just going to scratch that out. This script R is R minus R prime, and the length of it then in Cartesian form is this x minus x prime squared plus y minus y prime squared plus z minus z prime squared, 3/2. So a convenient way of trying to remember this is to start off with this, right? Phi is q over script r, and E is q r vector over r cubed. And the r vector, of course, is x hat, x minus x prime. So if you're trying to, I find this a little easier to remember and then work back from that. Okay. Very good. Okay. Let's see another couple of simple ones. Relationship, imperiometric relationship between E and phi. So this is not asking what is the the nature of E and phi. This is simply asking for the imperiometric relation between them. And then the next one is what is the formal definition of the gradient, which I already gave, right? We just talked about that. So let's skip down to, and the gradient in Cartesian form. Okay, we just did that. So how about, so I need somebody to do number 3 and number 7. Very good, Mr. Fox. That's right. The only improvement I would make on this, it's very good, the only improvement I would make is in your writing down the gradient. I would put the unit vectors to the left of the derivatives. Now in the Cartesian form, it makes no difference because the unit vectors don't change with position. And so really this isn't wrong, it's okay. But remember that the derivative operator acts on anything to the right. And so in this case, this would be operating on both this unit vector and this stuff here. But of course, the unit vector is a constant, so it doesn't matter. But when we go to other coordinate systems, the unit vectors depend on where you are in the plane or in the space. And so those derivatives of the unit vectors are not 0 anymore. And the usual form is to put the unit vectors over to the left of the operator so you don't have the derivative of the unit vector. Okay, so this is not wrong at all for Cartesian, but I'm just trying to get you into a habit that you can carry over into other coordinate systems. Okay, so that's the only thing I would do is get in the habit of putting the unit vector to the other side of the derivative, and then it's not an issue. Okay, because that's what you'll be doing later. Okay, and now we have, this one is the imperiometric relationship between the electric field and the phi. So what does this mean in terms of phi and the electric field, going back to the fundamental definition of the gradient? Right, what direction does E point?
Always increase.
Yeah, the opposite to the greatest increase, right? The opposite direction. So it's the greatest decrease. In other words, it's going to lower F. And then the magnitude is the slope of the phi in that direction. Okay. And then number 7 was just putting that using the component form. So this, our result here says, this answer here says that the direction of greatest decrease is along negative z hat. And you can see that here, phi here depends only on the z, so there's no change in phi in those directions. And if we look at phi going as a function of z, like this. And then actually, we'll for negative, for negative z, it'll actually go back up like that. I think that's right. No, that doesn't look right. That does not look right. Hang on. Not quite. There's no cusp. It must be like this. Here we go. It goes like this. Okay, that's what it looks like. It's linear outside here, so it's linear function. Okay? And so the electric field here, this result has got to be the slope of this function, the negative slope. And it doesn't depend at all on x and y. So this phi only depends on z, and so the electric field is in that direction. Okay, good. Oh, I keep doing that. Okay, let's see, where are we? Formal definition of the divergence, we've done that. Express the divergence in Cartesian form, we've done that. Any questions about that? Okay, here's a little bit more challenging one. Find the volume charge density that generates this electric field in Cartesian form, where E naught and A are both constants. So I need a volunteer for that. And then we're going to have a problem now where we have a dipole straddling the xy plane. And we want to find the electric field in that plane everywhere, which means as a function of x and y. So, 2 volunteers. Mr. McKenna? Somebody for number 11? Come on, Ms. Weaver. There you go. Good. Thank you. Okay, this looks fine. So she's drawn the 2 charges present, and then she's constructed the electric field due to each charge. Over here, if we have extend, say this is the x-axis, suppose we have a location right here. We want to know what is the electric field here. So, oh man, how did that happen? There we go. Okay, so the electric field here will point away, the electric field generated by the positive charge, and the electric field generated by the negative charge will point towards. What is the relative strength of those two electric fields? Pardon? The relative strength is what I mean. How does E1, the magnitude of E1 compare to the magnitude of E2? They're the same, because the charges are of the same magnitude and they're the same distance from this point. Those charges are the same distance from this location. So those are of the same magnitude. And they're pointing, notice in this case, they're pointing somewhat in opposite directions. The component that isn't opposite is in the negative z-hat direction. So it points downward, which makes sense because the electric field generally will point towards the negative away from the positive. Right? So you have this electric field pointing downward here. And notice that the x and y components of all these things cancel out exactly. And so it's quite simple. The electric field is quite simple. Okay, any questions about that? Mr. McCoe?
Yeah, how is the dq negative on both sides? Like on both charges, I guess.
Okay, so let's see. Up here, wish I could have a red pen here so I could write without altering here. Remember, the relationship is x minus x prime plus y. Y minus y prime plus z minus z prime. This is in the numerator, right? So what is the x prime coordinate? That is the x of the charge. In both cases, it's 0, right? For both charges, and y prime, both 0. And z prime for the positive charge is d, and for the negative charge is negative d. And so that's why we get it's a negative z prime here, so it's z also. Z is 0 because we're evaluating the points only in the plane. So z is also 0. So in one case we have q times negative d. That's the first one. And the second we have negative q times positive d, because it's the negative of the negative. And so that's why we get 2. So you got to keep track of signs and things, right? It's just something you need to learn how to deal with, so that you don't accidentally, end up canceling the z parts and getting an xy electric field in the xy direction. It'd be quite easy to do that. Also, don't overthink these questions. If I say, for example, calculate the electric field everywhere on the xy plane, you might think, well, it's got to be the same everywhere, and so I can just pick one point and do it at one point. That's not what I mean by this. I really mean you can find the electric field everywhere on the plane. It's a function of x and y, right? This serves for every point on the plane. Okay, so the next one is find the electrostatic field for that problem, and then the total potential energy is stored in this arrangement. So 2 more volunteers. Oh, let's see. I'm sorry, I didn't go over Mr. McKenna's here. Hang on a second. Let me do this before we jump. Yeah, so his row is better there, so shave off a little piece there. Give it a shave. cut too much hair on the row. And okay, but look, you got better. And so okay, I would say here. Anybody see? I want to. There is something pretty clear here. I want to improve on this first line. It occurs twice.
Oh, yeah, dot between.
You need a dot there, yeah. Remember, when we were doing vectors, I said don't write 2 vectors side by side like that. That's not a dot product or a cross product. It's going to be used for something else called a dyad, and it's a tensor, and you don't know what it means yet, right? So probably, but maybe you do. But in any case, we're not doing tensors yet in this class. So don't put vectors side by side. Give it a specify the kind of product, which is either going to be a dot product in this class, either a dot product or a cross product. Okay. And the same is true for this del operator. Remember, we've got a divergence of a field or the curl of a field, and this thing is going to be something else. It's not what you might think. It's neither one. Something of both, actually. But anyway, don't write that way. Okay. And then he just carried out the derivative in Cartesian form. Pretty simple field. This is a strange looking row. If you were to try to plot what this looks like, where the charges are, it's kind of funny looking. Okay, but it's mathematically simple to take the divergence, so that's why I got that function. So there are two parts. The first part is remembering Gauss's law. If I have the electric field, I can find rho from Gauss's law, or Maxwell's first equation. And the second one is actually carrying out the divergence. So there's really two parts to that problem. All right, looks good. All right, last two problems here. I'll calculate the electrostatic field and calculate the total potential energy of this arrangement of charges. Okay, now why has this pen suddenly stopped working? There we go. Okay. Volunteers, come on, just two more. Everybody's looking down. Mr. Heskin's looking straight up. You've already done your. I want somebody who hasn't had a chance yet.
I've already done.
Oh, you did one?
It was the.
Oh, it was really easy though, wasn't it?
Like weird.
All right, but that's what you get for volunteering. You get to pick the one you do, right? So, Mr. Field, you like to give it a try?
I'll give it a try.
All right, please. Well,
I'll do it if I can volunteer again.
you can volunteer. No, I want to see if I can get somebody who hasn't volunteered yet. Ms. Myers, you're reliable. Come on, somebody who hasn't had a turn. All right, we got 10 minutes. Think about it.
I have a question about number 10.
Okay.
So,
Number 10 was which one? The electric field? Oh.
would you not
Find the the bond charges. Yes, sir.
would you not need to state the x hat and y hat directions in this?
No, right? So the question was, in calculating rho there, you've got the divergence of the electric field, and what happened to the directions? Remember, the divergence of a vector field is a scalar. There's no direction associated with it. So let's think about, remember what the divergence means. Fundamental definition of the divergence is I want to find the divergence right at this point, so I'm going to surround it with a volume that completely encloses it. Could be a sphere, could be a cube, doesn't really matter. And I want to know what is the flux of that field coming out through that surface. And I completely enclose that region so nothing escapes. Whatever's coming out, you capture with this. And so I find the flux, and then I divide by the volume, and then I shrink the volume down, keeping it, corralling that point, take that limit. And so that flux does not have any direction associated with it, it's just what's coming out, right? So the direction is implicit there, and the divergence is what's coming out. But out, in that sense, means coming out this way on the top, and this way on the bottom, and this way over here, and this way over here, so you just add those all up. So there's no, and in the Cartesian form of the divergence, remember you're taking the dot product of the del operator with the vector field, so just like the dot product with two vectors, there's no direction left. Right? You get the sum of the products of, you get the sum of the sum of the products of the corresponding products of the Cartesian components. Remember, when we did the dot product of two vectors in Cartesian form, it's just the sum of ax bx plus ay by plus az bz, right? And so the same thing when you do the divergence, say, of b, it's dbx in the x direction, dby in the y direction, and dbz in the z direction. Okay? So in this case, the electric field was x squared x hat minus y squared y hat plus xyz hat, and then multiplied by some constants that just go along for the ride. The divergence then of this. So you have, I'm going to pull out the e naught over a squared. That's a constant, so I'm going to pull it out here. So you have the derivative of of the x component with respect to x, the derivative of the y component with respect to y, and the derivative of the z component with respect to z. So this is where we get the 2x minus 2y, and this is 0, because x and y don't depend on z, and no direction left. Okay? Okay. So here is the electrostatic potential. Comes out to be 0. Let's see now. Okay, aha! Very clever. Okay, very clever. Is that really, Oh, I see. I see what you did. Okay, all right. This takes a little bit of thinking, but you did it in a very. I'm going to say here what you want is you want a dot product here. Remember, this is a work. It's related to a work. So, are you bringing it? So you're bringing it in. If I understand, maybe I should just let you explain it.
I didn't know the best way to sort of reverse the del operator, so
Okay.
I did an integral, but
Okay.
I don't know if that's the best way.
All right. So you're calculating the work done, or what would be the work per charge, done by the electric field moving the point charge in from infinity. I'm thinking. Okay, that would be the closest thing I could reason for this. All right, but in this case, your displacement is in the z direction, so you're moving it from way above or way below, perpendicular to the plane, and you bring it down onto the plane. Okay. But then you notice that when you do this integral, yeah, the problem is, okay, it doesn't work. What you want it to do, it could work, but it doesn't work. And that's the reason if you're moving it from above the xy plane, here are the charges. If you're moving it from way up here down onto the plane, to some place on the plane, the problem is you need the electric field, you need to load the electric field up there. But we didn't find the electric field up there. We found the electric field only on the xy plane. So we did not find the electric field as a function of z. Now the other way you could do this, though, so that would work in principle, but you have to know E of x, y, and z. And you don't know the z dependence. So that doesn't quite work. You got the right answer. It doesn't work.
Yes.
Wrong reason. Okay, the other way you could do it, here's the dipole again. You could move it from way out along the x-axis and move it in to some place, or any place far away and move it in to some point on the xy plane. So there's the plus q and minus q. And you could move it here to some place on the xy plane, but you do it inside the xy plane. You have the electric field everywhere. Okay, so suppose but if you're moving in, notice that the displacement, in which direction is the electric field? It's always this way. Excuse me. My reminder. Okay, but the displacement here is always going to be perpendicular to the electric field. The electric field is always pointing down, and the displacement in the plane will always be perpendicular. And so this integral of E dot dr will be always 0, because E is always perpendicular to motion in the plane. Okay, so that would, you have E everywhere on the plane, so you can't do that. And that would show that phi is a constant, which would be 0, because that's choosing the constant at infinity. Okay, now this is a hard way to get it. There's a much easier way. Mr. Bicot.
You know, just add them.
Yeah, right. The integral's already been done for you, right? Remember what the electrostatic field is for a single charge? It's q over the distance. And so I have two of them now. So we want q over the distance. So the first charge, phi 1, is going to be plus q over the distance from any point on the xy plane to that charge, which is then x squared plus y squared plus d squared. And then phi 2 will be minus q, and then the distance from that from the point on the xy plane to that other charge. Remember, we said those distances are the same. The charges are opposite, so when we add these together, we get 0. In general, you can see that if I have a dipole like this, a plus q and a minus q, and if I have the line, that bisects those two, phi is 0 on that line or that plane, because every point on that plane is equidistant from the two charges, and they have opposite charge. So there's going to be, phi will be 0. Does it? Now phi will change if you go off of the plane, because there's an electric field, right? So phi is changing perpendicular to the plane, but in the plane, it's 0 everywhere. Okay, questions about that one? Does everybody understand why? Okay, the last one then is the total potential energy. What is the total potential energy? Well, okay, remember, F and V involve two charges, a product of two charges, two charged bodies, whereas E and phi involves only one charge. That's the distinction between phi and V. V is a potential energy, phi is an electrostatic potential. And now we're asking, going back to the mechanics, what is the potential energy of this arrangement of two charges? Okay, anybody remember what that is, Mr. Picot?
Is the charge times phi? The charge, the other charge.
We could, for example, calculate the electrostatic potential at this location because of that charge, and then multiply by Q. We could do that. Okay, so if we do that, let's calculate phi at this location because of that charge. So it's negative Q divided by the distance, which is 2d. And now V would be Q phi. So it'd be minus Q squared over 2d. Yes. If we calculated phi down here, phi up here would be negative Q over 2d. Phi down here is plus Q over 2d, right? So this would be phi at 1 and phi at 2. But then we would multiply to get the potential energy, we multiply by negative Q, so it would come out to be the same potential energy for the two cases. The easy way to remember it is just the product of the two charges divided by the distance between them, whatever that is. And the distance is 2d, and each charge is Q or negative Q, so that's why we get this. Okay, so you can reason it as Mr. Picot did. You could reason it that way, or you could remember that the potential energy of two separate charges separated by distance is just the product of their charges divided by the distance. It should all come out to be the same, either way you do it. Okay, questions? Good to go? So remember, this is to give you an example of the kinds of stuff. The questions won't be the same, and there may be things that are not on here that are fair game, right? But the imperiometric gives you a pretty good idea of what kind of things to expect. There'll be different vector forms or something. You're still going to need to take the gradient of something, take the divergence of something. Remember Maxwell's equation, first equation, Gauss's law. Yes, sir.
Can you explain the formal definition of divergence?
Formal definition of divergence. So we go back. There is the formal definition of the divergence right here. And with your permission, I will send out this podium notes. I know some people have written down on here, but it's within the family, right? So I'm going to send it out. And I'll try to get this down as PDF as well. It's in that, if I can do that. I don't know how to do that, but I'll try. So I can do it with this one. There's the formal definition. Remember, it's the shrink wrap process. You completely encase the point that you want to know. It's like the derivative. The derivative in one dimension, to help explain this,